And I'm Shailendra Kadre, your host as usual. And welcome to iClub. And today we'll we'll see something hands-on related to LSA and LDA. So you might be wondering what is LSA and LDA. So LSA we had covered in the last class, latent semantic analysis. So latent semantic analysis is will be used to reduce the dimensionality of algorithm which we get after using TF-IDF vector. So with TF-IDF vector when create TF-IDF matrix for our vocabulary. So that will be huge actually. So we have to reduce the dimensionality. So for that we'll be using latent semantic analysis and latent directly algorithm LDA will be used to zero on a topic actually. Suppose there are 10 concepts. So we discussed yesterday theory class that this LSA returns concepts instead of topics. So concept means probable words which most accurately represent a document. So words which most accurately represent a document, that those are written by LSA. And out of that, we want to find out most probable word. So for that, we'll be using LDA. So what is that? So first half you have document, and for each document, say you have 10 concepts which are written by LSA. So 10 topics you have, and in that 10 topics, suppose you want to find out the probability which is most probable. So that we will get with the help of LDA. Okay, so there are two layers. First, we'll use LSA to get the concepts, and out of those concepts, whichever is most probable, for that we'll get our LDA will use. So both. So Dirichlet allocation is based on Dirichlet distribution, which is a very well-known statistical concept. So I will advise you to go through Dirichlet allocation and Dirichlet algorithm, Dirichlet distribution from the internet, and try to make yourself clear that what these two things are. So, see, Dirichlet algorithm is something which is a distribution. It tells you like which are the probable, like suppose there are 10 concepts which are zeroed by LSA. So out of that, which is most probable, so it will give a distribution to you, probability distribution. Suppose 10 you have 10 you have identified 10 concepts that they may represent a document accurately. So this you do with the help of LSA. Once you have those concepts, then you want to find out the probability of each. So that probability distribution is given by LDA. So LDA tells you which out of the concepts which you found out by LSA, what is the probability of each concept having the properly representing the topic name. Okay, so these are the two things we will. So any questions still here? LDA, why we are using LSA, why we are using LDA? Any questions here, guys?
No, no, sir. It's clear.
Oh, yeah, it's clear. It's clear, right? Himanshu, it's clear, right?
Yeah, yes.
So now we do some usual imports. So let us directly jump into the notebook. So we do imports like NumPy, Pandas, Matplotlib, PyPlot, and then we import style, Seaborn, and then we say matplotlib percentage matplotlib inline to get our plots within the Jupyter notebook. Then we set style. So these are the two statements to set the style. Then we are then using some libraries related to NLTK. So we are importing NLTK stop words for removing stop words. Then we are using NLTK tokenize, and then we are using will not be using these stammers here. So we'll be using wordnet lematizer here. So these two imports are like they are done just they're unnecessary for this problem actually. They are not required. So we'll be using wordnet lematizer. Then this Shankar also we have not used. And then we will use this TF-IDF vectorizer. So these kind of when we do LSA and LDA analysis, LDA and LSA based analysis, we generally don't use count vectorizer. So we go only for TF-IDF vectorizer. So that I think you are already aware. And stop words. So now we are making an object of stop words. So set nltk.corpus.stopwords English. So we are getting English language stop words, and we are getting an object stop underscore words in which you have all the stop words are there. English stop words are there. Then you load the data set as usual. Read underscore CSV. When I display the head of the data set, it's a simple, very simple data set. You have headline, which date the headline was published. So it's a news related data set. So publish underscore date, so publish date, and then you have headline text. So publish date is not much useful for us in our analysis. So we drop publish date. So now we are left with only headlines. So that's what we'll be using, our headlines. So if you see that there are, I have not printed the shape here, but this headline shape is 1.2 million headlines we have. So it's pretty big data set. So maybe your ordinary computers with 8 GB RAM may not be sufficient for this. So I will recommend something like Google Colab Pro and those kind of cloud platforms to solve this problem, because there are 1.2 million headline sets we have. So it's pretty huge actually. So that's how we proceed. Then once we get this headline head, then we do some kind of data cleaning. So data cleaning is simple one step. First, actually, before using lematizer, we should convert it into lowercase. But what is happening here is, see, looks like all the news lines, like all the headlines, are already in lowercase. So this gentleman has not like we have not followed that dot lower step. We are not converted to lower. Directly we call lematizer, and then we lematize one by. We take headline one by one. We do the lematize. We lematize the words by taking by removing the stop words. So this particular line removes the stop words, and for every word we do lemmatization. And once we get that lemmatization, we make the sentence again by joining them by the spaces. So this particular will do that work. It will join all the words which are lemmatized. So it will join on spaces. Then you have the clean text. So without stop words and all words lemmatized. So this all two processing we have done. So it will return. So this function, now we take the entire column, headline clean text. So this we had a headline clean text. So headline clean text was a clean text is a new column we are creating. We're applying it on our original headline underscore text column, and we are using dot apply pandas dot apply method to apply this clean underscore text is a function. We wrote to redo the lemmatization and remove stop words. So we are applying. So this function will be applied to each and every row with the help of this dot apply method of pandas, which works on data frame. So once you see the data frame dot head, so now you have two lines, which is this is original and this is your cleaned one. So cleaned one is not having stop words and it is lemmatized. So this is what it is. So now then it is headline text. So these two we don't require. So the original we can drop. So original we have dropped here. So once we say, so now we have our clean text here. So dot head. So you can see the clean text here. Okay. So we have here, now we can do some processing on this. Just for displaying, we are displaying the first document after cleaning. So it looks something like this, like decides community, so decide community broadcasting and license. So we have removed the stop words and we did some nice lemmatization on this. So after that, we have this clean text. So this is first document, very first document. So now we want to extract features. So we are using TF-IDF factorizer. So you all know now because yesterday's theory class we had covered what is a TF-IDF, how to do TF-IDF factorization. So all those things will not be visible to you because of behind the scene, this particular method TF-IDF factorizer will do all the job. So we are choosing lost stopwords as stopwords. Stopwords is nothing but that object we made very first. Stopword object we made very first here with the English. See here we made the object instantiated NLTK using English. So this is the word. This is what we are using here. So this is what we are using here in our softwares. Then maximum feature equal to 1000. So features equal to 1000 means like when we do TF-IDF vectorization, we are keeping our maximum features like number of words. So our vocabulary we are limiting to our big of words we are limiting to 1000. So maximum feature equal to 1000. Then once you have the instance of this vector TF-IDF vectorizer, then you do fit underscore transform on clean text. So now you get the shape. So shape is very obvious. So these are 1.2 million documents, and each document is limited to 1000 features. So that's what you are getting. So it's a huge matrix of 1.2 million rows, and maybe 1000 columns. So as per my information, Excel can contain only 1 million rows maximum. So this kind of data set, this kind of matrix, or this kind of data set, if you convert it into data set, so you will not be able to accommodate in Excel, as per my information, because Excel can hold up to only 1000. So we need to reduce the dimensionality. So see, we need to reduce the dimensionality. So just we are telling the IDF values. So vector.idf values we are putting in IDF, and for every 1000 feature we have IDF value. Okay, so that we get vector.feature names. So 1000 feature names will be there, and for every feature we have IDF value. So this is what we zip, and then we sort it based on values. So here we get values and sort this dictionary. So first you see that police is for most. So we are printing L0 means highest IDF word, and -1 means least common word. So you can see that police is the most common word, and walk is least common word. Then we are printing simply taking the keys of police and forecast. We are printing their IDF values here. So this is what. Then we come to our main thing, topic modeling. So first we apply LSA to latest semantic analysis to reduce the dimensionality. Yesterday's theory class we had discussed that we use some kind of SVD, like singular value decomposition technique, to reduce the dimensionality. So we import here truncated SVD, and within truncated we instantiate truncated SVD with n components. Means from 1000 columns we are reducing it to 10 columns. So that's what each feature. So number of features previously here were 1000. Till here there were 1000 features. See here 1000 features we had. 1000 features we had here. So we are reducing it to 10 features. We are using, there are many algorithms for this SVD, truncated SVD. So we are using randomized one. I'm not going to details of this. So we are using a randomized algorithm of SVD, and then 10 iterations we are using, and then of course we are using random state so that we can maintain the repeatability. So then we do fit underscore transform on vectorized text. So this vectorized text was something which see here. So vectorized text was having a shape of 1.2 million rows into 1000 features. So this is what we got after vectorized text, what we got after TF-IDF. So this is 1.2 million rows and 1000 columns. So that's what we are taking directly here. And we are taking directly here, and we are reducing the dimensions. So we are reducing the dimensions. So this vectorized vector underscore text is having 1 million, 1.2 million rows and 1000 columns. So by using this LSA model, we are reducing the dimensionality to 10. So now you see the LSA top which you got after fit transformation. So shape is say number of rows remain the same. So number of rows are 1.2 million, and number of columns have been reduced from 1000 to 10,000. So if you want to just display top one, so let's say the top one first document. So for document 0, you have 10 concepts. So every concept is denoted by here topic. So maybe telling them topic will be wrong, so they should be rightly called as concept. So concept 0 to concept 10, you have these particular values. So we are multiplying it by 1000, and for each first document, that is first row of this LSA top, we are having these 10 concepts. So these 10 concepts are given by 10 concepts and their score. So these 10 concepts are given by LSA. So now next what we want to do, we want to find the probability distribution of these 10 concepts for every document. Why we want to know probability distribution? Out of these 10 topics, we want to find out which is the most probable topic. So for that, we will use LDA. So like LSA model, you have here components. So for each word, so each one of this topic, is a word, which we'll come to know later. So each one of this topic is a word, and that is represented by 1000 components. So the shape is not printed, but if you print the shape, it will be, let's say component of, say, number of topics. So number of topics and number of words. So number of topics is 10 and number of words are 100. So that will be the shape of this particular shape will print, 10 by 1000. So it is 10 topics. So these 10 topics, these are the 10 topics. For every document, we are having 10 topics. So the 10 topics are 10 concepts. So for every concept, we have, if you see their word vector, so it will be 10 by 1000. So till now, any questions here? So now what we do here, like get feature names, which will get 10 features, like vector. So vector was having 1000 features. Vector is our original vector which we instantiated before. That was our vocabulary. So it is having 1000. So this vocabulary will have 1000 columns, and these LSA columns will also have 1000 columns, right? We just saw that LSA model here is having 1000 columns each of the topics. So we are taking components in LSA model.components, and then we are zipping vocabulary and component here. We are zipping vocabulary and component, and then we are sorting it, sorting this particular dictionary based on these lambda variables. So lambda means x1 it will take. First, in this zip there are two, right? Vocabulary and component. So x1 will take the component, and based on that we are sorting in reversing order, taking the first 10 out of that. Once we take first out of the 10 out of that, you get in this form. So topic 0. So topic 0 is having this 10 probable word vocabulary. Topic 1, this vocabulary. Up to topic 10, you have vocabulary is given. Okay. So now you have topics. What we did so far is we reduce our TF-IDF vector. Whatever we got, we reduced it to column 10. So each column was the topic. So for each topic we got the probable words. So for each, so now we want to find the distributions. So once you want to find the distribution, means you want to apply LDA. So LDA you want to apply means you just instantiate first import Dirichlet allocation algorithm. You instantiate it with the number of components 10. So 10 columns. And there is a learning method. So there are many. So we choose online learning method, end of state, given, and we try only one iteration here. So when we do feed transform on original text, which was our, this vector is we got from TF-IDF. So we did feed transform of this, and then we saw the shape. So shape is again number of documents by number of, because see number of components we had taken 10 here. So number of documents 1.2 million and then 10 shape. So see here now the beauty of this is that if I take LDA top, so LDA top is nothing but my Dirichlet allocation, whatever I'm getting. So top, that is what is the metric. So previously whatever we did, we called it as LSA top. See, previously whatever we did, so we called it LSA top, right? So we called it LSA top. See here, that was with latent semantic analysis. Whatever we are doing with the Dirichlet allocation, that's what we are calling as LDA top. So LDA top, we are doing fit LDA underscore model, fit transform. Or this is this is the vector TF-IDF matrix we got. So we are using the original TF-IDF matrix here, fit transform, and we are getting our Dirichlet allocation. So shape. The shape will be again same. So shape will be same. So now, but if you take, see, out of this 1 million rows, if you take any rows, so say row 0, row 1, row thing, any of these 10 components, if you add the probability, so it will add up to 1. Why it will add up to 1? Because it is showing the probability. So probability C is sum equal to 0. I in LDA top, I'm taking the first element, only first one. So there are 10 columns. If I'm adding all the 10 columns, the value is 1. The value is 1 here. Okay. So now for document 0, we are taking. So LDA top is having 1.2 million rows. You see, LDA top is having, see, print if I say LDA top shape, if I'm printing, it is having 1.2 million rows. So each row represents one. Each row represents one particular document. So I'm taking one particular, first I'm taking first document by saying index 0. So first document I'm printing. So it is for document 0. So for document 0, I had 10 words, right? For every document, I had 10 words here. So see for document 1, so document 0 also I had 10 probable concepts. So I want their probability distribution, which is the most probable one. So when I do this particular, so which is the most probable one? So topic 8 is 62%. So that is what. So in document 0, topic 8. So topic 8 is a word actually. So that is having a probability of 62%. So now we are just same thing we applied it there, and see it's topic 0. So topic 7. So topic 8. So topic 8 means index 8, right? Index 8 means last but one. So last but one means topic 0 I'm taking. Last but one means hotel. So hotel is having the most probable concept. Means it is related to related to a hotel. So most probably the document 1, in document 1, your topic 0 is related to hotel. Similarly, we get distributions for topic. So I'm getting topic distributions here, right? So topic 8. So topic 8 is last but one, right? So topic 8 is last but one, this one. So document 1 is most probably represented by these concepts. And now you can use these particular words and give the title 2, document 0. So Melbourne, people, community time, final, royal rise, story, commission, game. So what do you think can be the topic using these words? These are the prominent words in topic 8. And our directly allocation algorithm tells that topic 8 is most probable for document 0. So using these words, now you have to decide, you have to use your brain to decide your Melbourne, people, community, time, final, royal, rise, story, commission. So you have to decide one topic name using these keywords. So Melbourne, so there is Melbourne community. So royal rise, I'm not sure what about. Can you guess what can be, what it can represent what? So someone, can you guess it can represent what? Melbourne, people, community, time, final, royal rise, story, commission, game. So first of all, there it is very clear that they are.
Some story related to Australia. Yeah,
So yeah, it is
Melbourne.
related to Melbourne people community. But then what is making some final royal rise story, commission, game. So they are talking about some game actually, finals of some game actually. So maybe so from these keywords we need to decide from these keywords we have to guess the prominent the title which suits document 0. So that's how we total word. So now you can visualize each of these topics. So this word cloud, see, this is just a simple method to represent word cloud. So first you sort them, sorted words, and for any topic you can represent. So see, if you say topic 0, so topic 0 is having these prominent words. So if occurrence frequency is more, the word size will be more in word cloud. So if you say topic 0, then it is these are Brisbane, COVID, and house, fire. So these are the most frequently occurring word. So in cloud, in the topic 1, so in topic 1, police, restriction, Victoria. So some kind of restrictions after crime or something they are talking about. So police is very prominently occurring. Restriction is very prominently occurring. So maybe in India we have section 144. So like that, there is something, some restrictions might be there in. They're talking about Victoria. So Victoria is I think is a city or a state. So Victoria is most probably a state in Australia. So they are talking about some restrictions there because a lot of time they are talking about police. So law and order. So similarly, we can see for topic 8 also. Like topic 8 is the most probable we said, na? So we can see word cloud for just we pass 8 here instead of 0. So instead of 0, if we pass 8, we'll see the word cloud for topic 8. So we can guess what they are talking about, which words are occurring most frequently in that particular document. So that's how is the complete analysis. Analysis is pretty simple. So only one method is a key method, which I would like to highlight here. So this is a key method actually. So in which we are finding the components. So LSA model components. So this will we are zipping vocabulary with component. Then we are sorting it based on values, and we are taking the top 10. So that's how. So this is a key method which you need to understand, and that is repeated twice here. Once here, once in LSA, and once in see LSA also. You see here. Okay, so that was LSA only. So that was in LSA. LSA it is repeated, so it is repeated in LSA, and after that we have represented in LDA. So, someone, can you summarize this particular analysis? What we have done so far? For others, can you summarize what we have done so far in the entire analysis? Can you summarize the steps? So okay, so I will take you one by one. So first some imports, then reading the CSV, then some data cleaning. So data cleaning is nothing but your lemmatization and removing of stop words. So we did some lemmatization here. Then we applied this function to the text. So we got the clean text. So clean. Once we get the clean text, then we drop the original text column. So we have the only cleaned column now. So we are just printing the 0 and see the what is how the first document looks like. So after cleaning. So after that we did TF-IDF vectorization. So TF-IDF vectorization when we did, so its shape will be 1.2 million documents by 1000 features. So why 1000 features? Because we selected 1000 features, max features equal to 1000. So it's a huge matrix. So we want to reduce the dimensionality. For reducing the dimensionality, we did some kind of reduce the dimensionality. We used truncated SVD, and we used the truncated SVD with 10, only 10. So you can play with this 10, you can use 12, 15, 20, whatever you want. But we reduced with the help of truncated SVD, we reduced the dimensionality. So this was the vector underscore VCT underscore text was our TF-IDF matrix. So that's what was 1.2 million by 1000. So we reduced it to 1.2 million by 10 columns. So if you see the shape of this 1.2 million, so shape is, see, so this is what reduced dimensionality. So we reduced it with the help of singular value decomposition, truncated SVD. Then we got 10. So these are all, so these are 10 topics we get out of this. So whatever this 10 is, so original words were under 1000 actually. So count TF-IDF values were given for 1000. So we reduced it for 10. So these are 10 topics actually. So these 10 topics values. And then when we see 10 topics, so each topic is having probable words. So for document, so this is for document 0 only we are talking about. So for each document we are having 10 topics or 10 concepts, and each concept will have 10 probable words. So these words are there; these are probable words. So once we do that, but which we don't know that out of these 10, which is the most probable topic. So which is most probable topic we don't know. So for that, we apply latent Dirichlet allocation, LDA. So applying almost methods are same, just you have to replace the method name with transform. And once you do so, see for document 0, we come to know that the probability of topic 8, so document 0 document 0 most prominently can be displayed, document 0 can be most nicely or most best can be represented by topic 8. So document 0 can be best represented by topic 8. So here that's what we see here, 62% probability, and all this topic probability if you add up, you will get 100%. So this is one. So this in terms of percentage, no. So you will get 100%. So that is the beauty of LDA. So then out of that, we want to know that what are the constituent words of topic 8. So that's what we did some coding here, and we find that topic 8 is having these words: Melbourne, people, community, time. So this is what LDA will give you. LDA will not give you exact topic, exact title of the document. It will give you some most probable topic, and from that topic you will have some words, constituent words, and from that you have to guess. You have to assign the particular title. So that's how this analysis works. So LSA we do LSA to reduce the dimensionality from 1000 to 10, and when we get say 10, so each one of them is 10. Each one of these 10 is one topic which can represent a document. So for each document we are having 10 topics, probable topics, which can best describe that document. And once you have that, we use apply LDA to find the most probable topic. So we say that topic 8. So now you devise a probable topic. So they're talking about some community game in which there is a royal rice story. So maybe some player is like performing great. So it's a commission game, and some player is performing game. So you have to devise from these words. You have to devise the proper title. So this is how this topic modeling works. And once you have that, you can write a small piece of code to give the like title 0. So title 0 is having prominent word as for COVID, fire, crash, coronavirus. So it is more about coronavirus in Brisbane. So document 1 is about Australia, because all the cities which we are talking about are in Australia. So this topic 0 is talking more about coronavirus, and topic 1 is more about police and restrictions. So maybe because of coronavirus, they have done some kind of restrictions, maybe some sanctions police have imposed on the city. So that's what they are talking about. So this is how you can guess. So similarly, if you run this particular analysis and just pass topic 8 here, so you will get word cloud for topic 8, which is most probable one. So I think that's how it is. So I stop here for a minute. If anybody has any questions, more than welcome to ask. So this is the end of our today's class. And of course, you have to spend some time on this code. And I want to give due credits to the creator of this file. This file was taken from Kaggle.com, and it was created by one gentleman called Raj Malhotra. So with due credit to Raj Malhotra, we have used it in our class. So it's a beautiful analysis done by Mr. Raj Malhotra. Okay. So any questions, Himanshu here? Any questions, Himanshu? Yes. So it's a two-step process. First, we find the topics using LSA. And in those topics, we want to find out the most probable one. So you use LDA for that. So you two-step process. So LDA, I think I have not covered in detail in the class. So you need to see what is the Dirichlet allocation and what is the Dirichlet distribution. See, Dirichlet allocation and Dirichlet distribution. I would request you to these are statistical techniques. So this I will. So let's see whatever we are getting here. Now this is whatever we are getting is a Dirichlet distribution for topic document 0. So it is a probability distribution. See, area under the probability curve is always 1, right? So if you see the area under this, so it will be either 100% or 1. So if you are representing in decimals, it will be 1. If you are representing in percentage, it will be 100. So it is probability distribution of topic 1 to topic 1, topic 0 to topic 9 for document 0. So you are getting a probability curve, and that is called your Dirichlet distribution, and in which the highest probability belongs to topic 8, which is 62%, clearly very high compared to others. And others are all almost equal, 4.158. So topic 8 is most prominent. And when you relate topic 8 to its constituent words, then you get these words. So as I said, these words. And from here, now you have to devise your own title using your own human intelligence. So that's how topic modeling works. So why we do topic modeling? There are, say, 10,000 documents, and you want to form, say, 5 or 6 clusters. And each cluster belongs to the documents which are having similar subjects. So you can do some kind of topic modeling using this kind of clustering can be done using this kind of analysis. If the topics are similar, they are put in a simple similar cluster. So similarly, you have 6 suppose you have 6 cluster of 10,000 documents. So there are 6 prominent titles, 6 prominent subjects on which these documents are clustered about. So that's how this kind of analysis. And cloud, this is a topic modeling is a unsupervised algorithm, because we don't do any kind of training. We don't have any any dependent variable to do. any kind of training. So it is unsupervised technique. We discussed all this in yesterday's class. And of course, now you need to spend maybe say half an hour, 45 minutes on this code once I share it with you. So you have to spend that time to fully master this code. It's not that 100% I have explained in the class. So some coding step you have to work out yourself. And if you don't understand, please bring them in the next class. Okay. So to help yourself, you have to read it. Okay. So that's how it is. Any questions, Himanshu or Soman?
No,
Himanshu?
sir, it was clear.
Himanshu, you understood?
Yeah, sir. Regarding that dimensionality reduction technique, the truncated SVD, what it is doing actually inside,
अरे भाई ट्रंकेटेड एसवीडी देखो मैं बताता हूँ.
like earlier we set this limit. This limit of 1000 topics. So why don't we initialize 10 over there only?
See, if we initialize, while doing TF-IDF, suppose we set these features to 10, you will be losing a lot of information. Document maybe say 300, 400 words, and you want to reduce it to 10, so you will be losing a lot of information. So this is very sparse information. That's what we are getting in the TF-IDF vectorizer. So when you do some kind of SVD, you see what you are getting. The 10 dimensionality which I have reduced. So I have not reduced the document and truncated the trailing one or leading ones. I have reduced, I got 10 topics out of that. So 10 topics out of that I got. So when I reduce with 10 topics out of that I got, and each topic is having some probable words. This is what I'm getting. So this is not a summarized information or value-added information? That's what I'm getting with LSA. So
Okay,
I'm
so
getting
this
topic.
is the prominent 10 topics.
Yeah, prominent 10 topics I'm getting. And for each topic, I'm getting probable words. So it's a concentrated information. That's what I'm getting with the help of my SVD, truncated SVD or LSA. Got it, na? And from Dirichlet allocation, out of these particular topics, I'm getting that probability distribution. See here, so this is the probability distribution of those 10 topics. So now I can choose 8 because probability is more. And from 8, I find out 8 has these kind of words. So 8 has this kind of words. So I can devise a particular title for this particular document. Got it?
Yes.
So I'm getting some kind of value-added information with the LSA. See, so LSA is giving me topics. So I'm not just truncating. I'm not blindly truncating the document. I'm getting value-added information. See here. So topic 0, probable words. Topic 1, probable words. So this is a value-added information which SVD is giving me. And now how exactly SVD works? So see, truncated SVD is giving, it is giving the statistical introduction also. So you see that in the vector form. So it is using, see. So then from truncated SVD, then he has come to the code part. So I think if you read the beginning para or something, what is this? Genpact. You got it, na? So if you use this particular, so this particular thing, if you read, I think you will get some idea about truncated SVD. Or if you want details, you can enter something like this. How truncated SVD works. How truncated CATD works. So recommender system. So see, in recommender systems also they have used SVD. So I think this only we are getting analytic India maxim. What is truncated SVD and machine learning? And, see, we are getting something. What is truncated SVD in machine learning? What is the difference between truncated SVD and PCA? So you have to do this some reading you have to do, yeah. So then medium term single value decomposition, truncated SVT and its applications. So I think this will give you, see, this is giving you more theory part. So you have to see all matrix form it is giving in a much detail. These kind of things you have to go through. It's highly mathematical actually. But if you want to understand, you have to break your head here. There is no other go.